This is Blueprint Reading 1, Chapter 7. This is course number 31442308. Last time we met, we started in on views with conventional brakes. We learned about brake lines. Today, we're going to kind of move forward with Chapter 7. We started a little bit with revolved sections, but let's review a little bit with revolved sections. So looking at figure 7.3 in your book on page 81, read along with me. The cross section shown for each shape is called a revolved section. Note in 7.3 that the section lines indicate the compensation of the structural shape. Revolved sections will be discussed in greater length in chapter 8. Again, if you look here at the revolved sections, what you can see is, for example, in example A, then you might notice that one there is a T-joint, which the revolved section is showing in the middle of the two brake lines. Now, if that revolved section wasn't in there, that could be mistaken for an angle iron. The same with going to example B in figure 7.3, the steel beam, that could be mistaken for a channel. Page 82, auxiliary views. Reading along with me. The preceding units showed that basic views can be used to represent an object, such as the front, top, right side, left side, bottom, or back. The proper selection and arrangement of several of these views are usually sufficient to represent an object. However, when an object has a slanted oblique face, an auxiliary view may be included on the print to show the plane of the slanted surface more clearly. Meaning, okay, so your blueprint has a flat surface and then it's angled on one side, but that angular part, looking at figure 7.4, okay, that might be the dimensioning coming straight up at an angle. If we looked at it in conventional methods, then it could be a little confusing. So what it can be done is repositioned for the auxiliary view. The auxiliary view represents a view of a slanted surface from a position at right angles, which are 90 degrees perpendicular to it. In figure 7.4, the surface represented in this manner is shown in its true size and shape. In any other view, this surface is distorted or foreshortened. So, auxiliary view would be bringing that angle to show you exactly how it would look in a regular view, so you can get proper dimensioning off of it. The development of the auxiliary view is sometimes shown by lines projected perpendicularly through the slanted surface. Usually only that part of the view that represents the slanted surface is shown. Now if you skip over to 7.5, a short brake line indicates the extent of the view. Dimensions are applied to auxiliary views in the same manner as for other views. Let me repeat that. Just because the object is shown in a different viewpoint, and here we're looking at 7.6, as far as dimensioning goes, that does not mean anything. Dimensions are applied to auxiliary views in the same manner as other views. So nothing changes, even though it's kind of broken away in as many, much like a detail view would be. These dimensions are the exact same as they would be in any other view. This here just straightens it out so you get an accurate viewpoint. The number of auxiliary views required depends on the number of slanted surfaces an object has. For example, 7.6 shows the auxiliary views used to show the true shape of each of the two oblique surfaces of an object. That's on figure 7.6. Okay. Going down to the use of both right side and left side views. In general, only a right side or left side, top and front views are required to show clearly all details needed to fabricate the part. However, when the part is very detailed, Both the right side and the left side are shown in addition to the top and the front views of the part. When both sides are included on the print, they are invariably shown as partial views. That is, whatever details are shown on the right side will not be shown on the left side, and vice versa. Presentation of the details in this manner makes reading the print much easier. Can you imagine if you had a bunch of details on the right side and a bunch of details on the left side, and then you tried to show them as accuracy on both sides? It would be, with all those hidden lines, it would make that blueprint a mess. So we have both a left side view showing only things on the left side, and then there's a right side view showing only things on the right side. And this is when you have both viewpoints. Looking at figure 7.7, as you can see there on the left side viewpoint, you have a left side, a front view, and a right side view. On the left side viewpoint, that left side end looks like a rectangle, and there we have the hidden lines showing the tubing or the pipe in the middle. But if you look on the right hand side viewpoint has a rounded object, but it does not show the left side view. It doesn't show the complete viewpoint of your object from the right hand side, because that would just make that part of it a mess. The same as on the left hand side viewpoint, you don't see hidden lines showing the right handed side circular part. So that is just to clarify things. Figure 7.7 illustrates the use of two side views in a front view. Note the detail that is eliminated from one side and is shown on the other side. This is just so everything becomes so understandable instead of just being a complete mess. Turning to page 83, alternate positions of a side view. As stated in Unit 1, the side view is normally found adjacent to the front view. However, when this location is not possible due to limited space, the side view is placed next to and in line with the top view. As a result, the space needed to show the three views is reduced. Looking at figure 7.8, note that the side view can be placed to the left of either the front or the top view. Alright, so let's talk about 7.8 here for a minute. Alright, the bottom viewpoint would be the regular. Okay, there you have your front view. Alright, and then you have your right side and your left side. Okay, but you could also have a top view, and say if you don't have space on your blueprint, then those side views could be moved up to the top view. So if they do get moved up to the top view, then they'll be shown as a top view as well. Alright, looking at figure 7.9, in large detail views, reading along with me. While prints may be drawn to a reduced, full, or enlarged scale size, parts are often shown in an enlarged scale. Meaning, so you have a print, everything is done to scale, but what if you have a little bit of an object that is just too small to see on the scale size used for the rest of the print? Then it becomes an enlarged viewpoint. The enlarged portion of the print, also called the enlarged detail, is shown as an additional view, usually located near the principal view to which it applies. Figure 7.9, the enlarged detail provides more space in which to apply dimensions and makes it easier to interpret the details of the area shown. To repeat that, the enlarged detail provides more space in which to apply dimensions and makes it easier to interpret the area shown. So what I was talking about before, to where, say you have a small part, and if it's drawn to scale as the rest of the print is too small to be seen, it can be enlarged and put off to the side to show the details better. So it'll have an enlarged scale size, just that little bit that you can't see in the regular scale side, and this here makes it easier to see it. and then it'll be as shown in figure 9. If you see that, it'll say see detail A or see detail B, so on and so forth. And then all you do is you just line that up to the part of the print. It says see detail A or whatever detail it addresses, and then that will show you the enlarged detailed print. Each enlarged detail is identified by a letter or number. The same letter or number is also used to identify the point on a principal view to which the detail refers. Now we come to one of my favorite viewpoints. These are called developed views. A developed view is also called a development. It is a view of a part as it appears when it is stretched or laid out on a flat surface. This viewpoint shows the part before it is shaped by bending, rolling, or any other fabrication methods. A developed view illustrates the part exactly as it must be prepared before any bending or rolling is performed. Looking at figure 10, 7.10, it may be very simple and involve only one bend, or it may be quite complicated and involve a series of bends, curves, and angles. It is common practice to show the location of any bends on the developed view. In addition, dimensions shown on the developed view include any allowances necessary for bending. So, let's look at figure 7.10. Alright, now looking over here on the left side of figure 7.10, here you have our material. We have our front view, we have our right side view, and we have our top view. And here we have bends and curves, trying to figure out that steel and figure out the full measurements and the length of the steel by using all this can be pretty confusing. So what we have is a developed view looking at it from the right side, on the right hand side. And here you have the dimensions, and again this here gives you allowances for the bending process, but it'd be the same thing as, alright, it's flattened out. That's the developed view. It's just flattened out, and then it gives you your measurements. And then over in the left side of figure 7.10, you can see where it all comes into play and what it actually looks like. But on the right hand side, there's your developed view showing the steel as it's flattened out. This is a process that is done for many tanks. All the blueprints in the tanks, when building fuel storage tanks, those are all flattened out as well. Speaking of that, looking at figure 7.11, here's a tank itself, and then here you have a blueprint, a pictorial view, and then you have a top view, and then you have the front view of a tank. Okay, and we're looking at the right hand side of figure 7.11, and there to where the front view. Let's look at that a minute. Alright, so here we have to where it's connected, we have a top. There's in the front view, you can see all the object lines showing the bottom of the tank, the top of the tank, and here in the pictorial view showing what it looks like, going up in the upper left hand side of figure 7.11. In the pictorial view, you see what it looks like, you know, as a finished product, not one that you would work on. But going over here, there you have your top view looking down at it, and then but over here in the front view, you see object lines, you see hidden lines, you see holes for flanges that are going to be cut out. It is just a mess. Now, as a welder, how would I come in and figure out how to build this tank looking at it from the front view? I couldn't. So I need a developed view looking at it to where it is flattened, laid out. It gives me an idea to where I can find in the developed view, I can find the center of those holes to cut, which would make it impossible if I was trying to go off of the front view, I need this developed view. Okay, now you do notice that in figure 7.11, look at the holes, they're kind of egg-shaped. That's because it is flattened out, and the rounded in the front view, they do become rounded. A developed view is also used to indicate the location of holes in sheets or plates that are to be rolled or shaped into cylindrical forms. Sorry, I mispronounced that. Figure 7.11. Holes, sizes, and location dimensions may be given either on the drawing of the part or on the developed view. It is not necessary to give the dimensions on both. In many cases, a developed view is absolutely necessary. For example, the following shapes all require developed views for fabrication. Fabricated angular pipe joints on which the sections are rolled from sheet or plate, or fabricated spheres, curved domes, or heads. Looking at figures 7.12 and 7.13, notice in figure 7.12 that the dimensions added to the developed views follow the baseline system of dimensioning. And there's your formula right at the bottom of page 84. Now let's go to revolved views. When an object is shown in true projection, it is drawn in all views as it actually appears. However, in some cases, one view of the object may be shown as it does not actually appear. For example, in a revolved view, a portion of the object is rotated in order to obtain a straight axis. In this position, the true shape of the object can be determined. This is done to give a more complete description of the object and to make the drawing easier to read. Although this is considered a violation of a true projection, it is nevertheless preferred, as shown in figure 7.14. Alright, so looking at 7.14, you can see the true projection, and then as looked at by the rotated projection, you can see to where it would be kind of a mess trying to figure out how things look in the true projection. The rotated obviously shows why it is more preferred. Note in figure 7.14, there is considerable detail shown where the angle iron and the small pipe join the larger pipe. Also, the larger hole in the angle iron is not shown in its true shape. In figure 7.14b, there is much less detail where the parts are joined and the hole is shown in its true shape, thus simplifying the interpretation of the lower view. Going on to true projection. Now this is on a blueprint to where I remember back to chapter 1, we had prints to where we'd have items showing hidden lines, such as like a lap joint would be one. Okay, now would you show the hidden line on the other, even though your object line lines up perfectly with a hidden line? Those would be what we saw before. Those are called true projections. It is possible that lines representing two different surfaces of an object shown in one view would, when shown in another view, appear as one line. This tends to make the drawing confusing and more difficult to read. Therefore, one of these lines may be shown out of true projection in order to show the edges of two different surfaces, as illustrated in figure 7.15. This would really be more in the case of where, if, say, you in this here, all you have is a front side and a right side view as the object showing. Now, if you didn't have any other viewpoints telling you that that line would was in the same location as say a hidden line in the same location as your object line, as shown on the right side view, as in what we're looking at in figure 7.5, we did not have any other viewpoints to tell us any different, then we might see something in a non-true projection. Typically, we see things in a true projection simply because there are enough viewpoints on the print to show you otherwise, to show you that it would be the same line. But just in case it doesn't, be aware there is something called a on-true projection. Okay, looking at corrections and revisions on prints. Figure 7.16. When an error is discovered on a drawing while in use in the shop, quite often the error will be marked with a red or yellow pencil. Any such error is usually reported to the supervisor so that corrections can be made on future drawings or on the master drawing of the print used. When revisions are required due to changes in design, they are often made on the original copy from which the print was made. In some cases, the original size dimension will be removed and the new one substituted. When such a procedure is followed, a listing of the original sizes will usually be made on the drawing, as in figure 7.16. So all it means is if one little thing gets changed on a print, instead of redoing the entire print, then what it'll do is just make one small revision, a change, but it'll make note of that change, and it'll give you your new it'll give you your new size on the same print as the mistake was. So you'll see this every once in a while. Generally, revisions don't get too crazy, but sometimes I've actually seen revisions will be printed and reprinted out on the same. Just instead of writing things out in pencil. Alright, this ends chapter 7, and then we'll move on to tests at another time as far as going in discussing the tests themselves. So, alright, this ends chapter 7.